In 2014, YouTuber MatPat of game theory fame released a video trying to apply real-world physics to the iconic Bullet Bill from Mario. MatPat's findings claim that Bullet Bill was not deadly. Now, I've been skeptical of his results ever since watching the video almost a decade ago at this point, and having a decent knowledge of physics, let's give this theory a little peer-reviewed study, shall we? Welcome back, one and all, ladies and 18th century artillery shells, to Mathamopoulos. Man, it's been a while since my last post. Let's just get straight into it. In MatPat's video, Game Theory, How Deadly is Super Mario's Bullet Bill, he tries to figure out if a bullet bill would actually be deadly like it is in the Super Mario Bros. Games. Now, this is an interesting question, and if there's one person qualified on this earth to try to overcomplicate a shower thought and apply real-world math to a fictional scenario, it's me. To start, first we need to figure out a scale factor. We need to know just how big everything in Mario actually is. You see, MatPat already did this, but this was before Nintendo revealed Mario's official height, so his scale factor is actually slightly off. Mario stands in officially at 1.55 meters when on shrooms and about 0.775 meters in his mini form. Dividing his height of 0.775 by the height of his sprite in pixels, we get a scale factor of this number. All future measurements will be based off this scale factor, as MatPat's scale factor is based on an incorrect Mario height. But it really wasn't his fault, and he actually got pretty close, about 16% error. Let's find out how fast Bullet Bill moves. I couldn't find any numbers about this on the internet, so I had to resort into digging decompiled source code of the original Super Mario Bros. Yeah, I dug through the actual source code to find out how fast a fictional bullet travels in a 40-year-old video game. If that doesn't deserve a subscription, I don't know what does. Through my digging, I ended up finding this little note. This is exactly what we need. That's why if you're coding, you should always comment on your lines. It's to help explain your code to people in 40 years in the future trying to make a YouTube video. But what does this number actually mean? Money sign E8? Well, this is actually an 8-bit hexadecimal value, so I gotta explain that real quick so we can figure out what the heck this says. So you know how our normal number system is a base 10 number system, meaning it uses 10 symbols, 0 through 9. Well, hexadecimal is a base 16 number system, meaning it uses 16 symbols, 0 through 9 and A through F. The format of this 8-bit value is as such. Each of these two hex digits is 4 bits in binary, meaning 1, 1, or 0. So now we take our value, E8, and we convert it into binary. And after that, we need to convert our binary into a decimal number, so we could actually understand this in numbers that we're more familiar with. So if we divide the decimal equivalent of each hex digit repeatedly by 2, we end up getting the binary equivalent number. But wait, how do we know if this number is positive or negative? We have to check for that before we convert it into a number that means literally anything to us. So we need to use the 2's complement method, because the code of Mario uses signed binary. If you've ever wondered how negative numbers are represented with just ones or zeros, this is how. If you don't spend all your time thinking about math like I do, you probably haven't, but that's okay. Signed binary is a pretty ingenious system which allows binary to represent a range of positive and negative numbers. In 8 bits, you can represent 256 different numbers, 0 through 255. In signed binary, this is split using this equation. So when you plug in 8 for n, which is the number of bits, you end up getting a range of negative 128 to 127. So to check if it's a negative, simply check the most significant bit. If it's a 1, it's a negative number. And would you look at that, our number is negative. To convert a negative 2's complementary number into English, first we need to flip all the bits, 1s to 0s, 0s to 1s. Then we add 1, so we end up getting negative 24. So after all that, we have 24. 24 what exactly? Jelly beans? Well, this number is actually measured in subpixels per frame. What does that mean? I'm sure we're all familiar with pixels, those little squares that make up screens. The original Super Mario Bros. Tracks positions using subpixels. Because the resolution was so low, they wanted to get more accurate positioning data, even if the visuals couldn't really represent these positions properly. So a subpixel is 1/16th of a pixel. Frame rate is how many times the screen is redrawn and updated per second to make it seem like the funny mustache man is moving. So the NES original ran at 60 frames per second, at least here in the US. There are 16 subpixels in a pixel, so Bullet Bill is moving at 1.5 pixels per frame. Now, using our pixel scale factor from earlier, we can solve for Bullet Bill's velocity. So 1.5 pixels per frame times our scale factor times 60 frames in 1 second. Looking at our units, pixels cancel out, frames cancel out, and we are left with 4.36 meters per second. Now, this number is actually kind of shocking. The reason why I'm so shocked is because MatPat calculated the Bullet Bill velocity as 30 miles per hour, or about 12 meters per second. And actually, our scale factor was bigger than MatPat's, so I thought our speed should actually be larger than 30 miles per hour, which was so unbelievably wrong, I guess. At first, I thought I may have miscalculated the pixel velocity of the Bullet Bill, but we can actually confirm by watching a recording of the original game and going frame by frame to see that in the game, Bullet Bill alternated from traveling 1 pixel to 2 pixels every other frame, which as an average is 1.5 pixels per frame. Considering MatPat said the Bullet Bill wasn't deadly at 30 miles per hour, it's not looking good, but considering the velocity error we discussed, maybe there are some other math errors if we keep going. Spoiler alert, there are. Next, we need to figure out how deadly Bullet Bobby Brown actually is. Remember the whole point of the video? Yeah. So this was one of the more difficult parts of the video, simply because, well, both MatPat and I overthought this. Now, some of you in the audience that have some level of physics knowledge might be saying to the screen right now, oh, it's just a simple collision problem, use momentum. But we need to cover some assumptions that MatPat makes to rule out this option. MatPat assumes that if Mario were to get struck by a bullet bill, and the game didn't end right there, he would stick to the bullet and be carried off screen with the bullet, meaning this is an inelastic collision. In a real-life inelastic collision, for example, think of someone getting hit by a car and sticking to the front end of it. If the car is traveling at a constant velocity before the collision, using this momentum equation, we can actually demonstrate the velocity must slow down because of the conservation of mass. Now, the key here is that we don't know Mario's mass or the bullet bills, and MatPat estimated these values, but I'd like to try and stick to confirmed values we know are true. So I'm going to make another assumption about this scenario that could make an equal amount of sense. We will be making the assumption that the bullet bill maintains its constant pre-collision velocity somehow, mainly because this will make our math much easier, and again, we don't have to assume values we really have no clue how to find. Now, I know I previously said that looking at this equation, it shows that velocity has to lower after the collision, and that is true, but only with objects that move at a constant velocity and don't accelerate during the collision. Going back to the car analogy, it's like if the man were to be hit by the car, and the driver were to give the car more gas the instant the collision happens to maintain a constant speed through the whole collision. Because of this, we actually can't use momentum, because momentum only deals with constant velocities. The assumption that Bullet Bill will maintain velocity makes sense within the context of the game, because we see that nothing can slow it down, not even hitting Mario when he has a mushroom. And at the end of the day, the final results really aren't that different between these two options if we were to estimate masses for both Mario and the Bullet Bill. Now that we got that covered, to actually figure out the lethality of a Bullet Bill, we need to calculate the G-forces of the impact. A G-force isn't really a force, it's an acceleration in terms of the acceleration due to gravity. For example, 5 Gs is 5 times the acceleration due to gravity. Car testing and safety ratings often use G-forces when testing the safety of new cars. So Mario goes from 0 to 4.36 meters per second practically instantly. That's where the lethality comes in. It's like the opposite of a fall. When you're falling, it's the stop that kills you, but in this impact, it's the rapid acceleration that kills you. Now, technically speaking, if this acceleration were to truly happen instantly, then Mario would be turned into a raspberry paste. The G-forces on Mario would be infinite, and that's not very realistic. So let's say the impact takes about 1 frame, so a 1/16th of a second. Using this simple equation, not whatever MatPat used. Seriously, what is this? Why is gravity here? We'll talk about this later. Anyway, using this simple equation, A equals V over T, we can find the acceleration it takes to bring Mario's speed from 0 to 4.36 meters per second in a 1/60th of a second. And dividing that number by 9.8 meters per second squared, we can find the G-force value. In these numbers, we get a drum roll, 26.7 Gs. Now, that really doesn't seem like a lot when considering a 65 G impact is considered fatal.
Hold it!
But it is still significantly more dangerous than MatPat's initial conclusion. A frontal chest impact is not likely to kill, so MatPat got that right. But with his math, it shows that the impact wouldn't be able to crack a rib, which is false. With this amount of G-force, you would actually have a moderate chance of a minor rib fracture. If we were to estimate Mario's mass, we could actually calculate the force applied to Mario, but again, we don't really know this. We can, however, use the average mass of a human being and see how many newtons of force is felt. So the average mass of a person on Earth is about 62 kilograms. So using F equals ma correctly, I mean seriously, we'll get back to this, I calculated an applied force of over 16,000 newtons, which is significantly more than the estimated 3,300 newtons to crack a rib, and the 4,000 newtons required to break the femur. But this is the best case scenario. If you were to actually sprint full speed into one of the bullet bills, Mario's top speed is about 11.625 meters per second. The chances of death are very likely, almost a 100 G impact, which is instantaneous death. See, because we already established that the bullet bill doesn't lose speed and practically can't be stopped by hitting Mario, the acceleration applied to the body would be much larger. It would have to completely switch the direction he's going in a 60th of a second. That's if it were to hit you. Mario really actually shouldn't die from this impact because of his bones. Initially, I thought Mario would be at greater risk because he's so small, but the gravity in Super Mario Bros. 1 is actually like 7.8 times larger than gravity on Earth, meaning his bones would likely be much stronger than a normal human's because his body has to be able to withstand the forces of gravity and survive jumping around the Mushroom Kingdom. So I guess in the end, MatPat stumbled into the right answer, kind of, but he has all the wrong justification. If you were just standing still, yeah, Bullet Bill wouldn't kill you most likely, but it's still dangerous, and if this were a math test, he wouldn't get full credit for his work, but he definitely deserves some partial credit for sure. In all fairness, at the beginning of the video, MatPat did say that this was impossible and he would try anyway, so I admire him for that. So where did MatPat go wrong, and why do I think my math is more substantial? Well, we already covered the size issue and Bullet Billy's speed, so let's move on to the physics. Oh boy. First time I was rewatching this, I was genuinely so confused where he pulled this equation out of. He overcomplicated this so much and tried to deal with air resistance, even though the bullet is moving at a constant velocity. I think he tried calculating the force Bullet Bill applies to counteract air resistance to move at a constant velocity, which he wrongly equated as the force Mario felt, which is not how that works, even in the slightest. Seriously, there isn't much explanation of where this formula was derived from, but every person, teacher I talked to, every bit of research and reference material I consulted agrees with my theory over his.
But hey, that's just a theory. A game theory. Thanks for watching. Man, I always wanted to do that.
If you made it this far into the video, seriously, thanks for watching. If you liked what you saw, drop a comment or a like, or maybe even subscribe? Now, this video isn't meant to throw shade at future 48th President of the United States, MatPat. That's why we have peer review to confirm results and data. So MatPat, if you are watching, enjoy your retirement from this wretched platform. Godspeed. To everyone else, be smart, be safe, and don't do anything too stupid.